Section 2.10 Entropy rate of a stationary source. In most communication systems, communication takes place continually instead of over a finite period of time. Examples are TV broadcast, the internet, and cellular systems. In a cellular system, people make phone calls 24 hours a day. For such cases, the information source can be modeled as a discrete time random process x sub k, k greater than or equal to 1. The process x sub k is an infinite collection of random variables indexed by the set of positive integers. The index k is referred to as the time index. Random variables x sub k are called letters. In this discussion, we assume that the entropy of x sub k is finite for all k. For a finite subset A of the index set k such that k greater than or equal to 1, the joint entropy h of x sub k, k in A, is a finite quantity because the joint entropy is upper bounded by summation h of x sub k, k in A, by the independence bound for entropy. This summation is finite because each term in the summation, that is, h of x sub k, is finite, and the number of terms in the summation is also finite. However, the joint entropy of an infinite collection of letters is infinite, except for very special cases. In the simplest example, x sub k are IID, and so the entropy of x sub k is equal to a constant h for all k. In this case, the joint entropy of x sub k, k greater than or equal to 1, is equal to summation entropy of x sub k, k from 1 up to infinity. Because x sub k are IID, that is summation h for k from 1 up to infinity, and this is equal to infinity. Therefore, in general, it is not meaningful to discuss the joint entropy of an information process. We are now motivated to define the entropy rate of an information source, which gives the average entropy of a letter of the source. Here is the definition. The entropy rate of an information source x sub k is defined as h sub x equals the limit as n goes to infinity, 1 over n, times the joint entropy of x1, x2 up to xn, when the limit exists. When the limit does not exist, the entropy rate of the information source is simply not defined. Note that inside the limit, 1 over n times entropy of x1, x2 up to xn is the average entropy of a letter of the first n letters of the source. In the next two examples, we show that the entropy rate of an information source may or may not exist. We first look at example 2.55. Let x sub k be an IID source with generic random variable x. Then the limit as n tends to infinity, 1 over n times the joint entropy of x1, x2 up to xn, is equal to the limit as n tends to infinity, n times the entropy of x, the generic random variable, divided by n, because x sub k is an IID source. Upon cancelling the n's, we have limit n goes to infinity, entropy of x, and this is simply equal to entropy of x. That is, the entropy rate of an IID source is the entropy of any of its single letters. In the next example, we show that the entropy rate of an information source may not exist. Let x sub k be a source such that x sub k are mutually independent, and entropy of x sub k is equal to k for k greater than or equal to 1. That is, the entropy of the letters are increasing with respect to k. Then 1 over n times the joint entropy of x1, x2 up to xn is equal to 1 over n times summation h of x sub k for k from 1 up to n, because x sub k are mutually independent. This is equal to 1 over n times summation k for k from 1 up to n. Now this summation is equal to n times n plus 1 over 2. Upon cancelling the n's, we have 1/2 times n plus 1, which does not converge as n tends to infinity, although the entropy of x sub k is finite for all k. Therefore, the entropy rate of the information source x sub k does not exist. Toward characterizing the asymptotic behavior of an information source x sub k, it is natural to consider the limit x sub x prime equals limit as n tends to infinity, the entropy of xn given x1, x2 up to xn minus 1, if the limit exists. The quantity inside the limit is the conditional entropy of the next letter, given that we know all the past history of the source. H sub x prime is the limit of this quantity after the source has been run for an indefinite amount of time. A fundamental question is H sub x prime equal to H sub x, the entropy rate of the source? A stationary information source is one such that any finite block of random variables and any of its time shift versions have exactly the same joint distribution. Here is the formal definition. An information source x sub k is stationary if x1, x2 up to xm, a block of m random variables, and the shift of this block of m random variables by L time indices, that is, the block of random variables x1 plus L, x2 plus L, all the way to xm plus L, have the same joint distribution for any block length m and shift L greater than or equal to 1. Here is an illustration. Consider the information source x sub k. Here, x1, x2 up to xm is a block of m random variables. By shifting the time index by L, we obtain the block of random variables x1 plus L, x2 plus L, all the way to xm plus L. If the information source is stationary, then these two blocks of m random variables have exactly the same joint distribution. Recall that h sub x prime is the limit as n tends to infinity, the entropy of xn given x1, x2 up to xn minus 1. The next lemma says that if x sub k is a stationary source, then the limit h sub x prime exists. Here is the proof of the lemma. Let us display the definition of h sub x prime here. Since the term inside the limit, which is a conditional entropy, is lower bounded by 0 for all n, it suffices to prove that this quantity is non-increasing in n to conclude that the limit h sub x prime exists. The idea is that for any sequence that is lower bounded, if the sequence is non-increasing, it must converge to some value. Toward this end, consider the entropy of xn given x1, x2 up to xn minus 1 for n greater than or equal to 2. By removing the random variable x1 from the conditioning, We obtain an upper bound because conditioning cannot increase entropy. In the next step, we downshift all the time indices by 1. That is, n becomes n-1, 2 becomes 1, 3 becomes 2, and n-1 becomes n-2. By doing so, we do not change the value of the conditional entropy because we assume that the information source x sub k is stationary. Therefore, the entropy of xn given x1, x2 up to xn-1 is non-decreasing in n, and so the limit exists as n tends to infinity, which by definition is equal to h sub x prime. The lemma is proved. We now introduce a notion called the Jizarro mean. Consider a sequence an, n greater than or equal to 1. Now construct another sequence bn, n greater than or equal to 1, where bn is equal to 1 over n times summation ai, I from 1 up to n. Here, bn is the average of the first n terms in the sequence an. The values bn, n greater than or equal to 1, are called the Jizarro means of the sequence an. We are going to show in the next lemma that if an tends to a as n goes to infinity, then bn also tends to a as n goes to infinity. Here is the proof of the lemma. Since an tends to a as n tends to infinity, for every epsilon greater than 0, there exists an integer n which depends on the value of epsilon, such that the absolute value of an minus a is less than epsilon for all n greater than or equal to n of epsilon. Now for n greater than n of epsilon, consider the absolute value of bn minus a. Now bn is equal to 1 over n times summation ai, I from 1 up to n. For a, we write this as 1 over n summation a, I from 1 up to n. What we have done here is to take the sum of n copies of a and then divide it by n. Combining the two summations, we have summation ai minus a, I from 1 up to n, and by the triangular inequality, we obtain the upper bound 1 over n times summation absolute value of ai minus a, I from 1 up to n. In the next step, we break the summation into two parts. For the first part, we sum I from 1 up to n of epsilon, and for the second part, we sum I from n of epsilon plus 1 to n. In the second summation, the absolute value of ai minus a is upper bounded by epsilon, because here I is greater than n of epsilon. The number of terms in the second summation is equal to n minus n of epsilon, and so we can write the second term as n minus n of epsilon times epsilon divided by n. Note that the fraction n minus n of epsilon divided by n is always less than 1. And so the second term on the right-hand side is upper bounded by epsilon. In this upper bound on the absolute value of bn minus a, the first term tends to 0 as n tends to infinity because the summation is a finite summation with a fixed value, and so it tends to 0 as n goes to infinity. Therefore, for any epsilon greater than 0, by taking n to be sufficiently large, we can make the first term less than epsilon, and so the absolute value of bn minus a is upper bounded by 2 epsilon. In other words, for n sufficiently large, we can make Bn arbitrarily close to A. Hence, Bn tends to A as n tends to infinity, proving the lemma. Theorem 2.60, the main theorem of this section, says that the entropy rate x sub x of a stationary source x sub k exists and is equal to the limit h sub x prime. The idea of the proof is to use the stationarity of the source x sub k and the Cesaro mean. Here is the proof of the theorem. We have proved in lemma 2.58 that the limit h sub x prime always exists for a stationary source x sub k. In order to prove the theorem, we only have to prove that h sub x is equal to h sub x prime. For n greater than or equal to 1, we let an be the entropy of xn given x1, x2 up to xn minus 1, and Bn be 1 over n times the joint entropy of x1, x2 up to xn. By the chain rule for entropy, 1 over n times the entropy of x1, x2 up to xn is equal to 1 over n times summation k equals 1 up to n, the entropy of xk given x1, x2 up to xk minus 1. From the above, we see that the left-hand side is equal to Bn, and the term in the summation on the right-hand side is equal to ak. Therefore, we can write Bn equals 1 over n times summation ak, k equals 1 up to n. Therefore, the values Bn, n greater than or equal to 1, are the Cesaro means of the sequence an. From the definition of h sub x prime, we have an tends to h sub x prime because the term inside the limit is simply equal to an. For the last lemma that we have proved, the Cesaro means Bn also tends to h sub x prime, and so Bn, which is equal to 1 over n times the entropy of x1, x2 up to xn, tends to h sub x prime as n goes to infinity. This limit, by definition, is equal to h sub x. Hence, we have proved that h sub x, the entropy rate of the source x sub k, is equal to h sub x prime. This completes the proof of the theorem. The theorem we have proved says the following. First, the entropy rate of an information source x sub k exists under the fairly general assumption that x sub k is stationary. Second, the limit h sub x prime is an alternative definition or interpretation of the entropy rate of the source x sub k when x sub k is stationary. However, the entropy rate of a stationary source x sub k may not carry any physical meaning unless x sub k is also ergodic. For details, please see section 5.4 in the textbook.